Along everyone. You remember Introduction to Astronomy last month? I just did the brief introduction about the planets for the solar system, and Jonathan Park up from Hamilton this evening is going to extend that and give us some more little details and some interesting little surprises, interesting little things about the solar system. So welcome, Jonathan, and I'll hand it to you. Thank you very much for coming on.
My gift down here. Right, good evening. It's nice to be back up here. I think last time was February and I talked about the observable universe. But tonight's talk is titled Solar System Surprises. So this is about some of the not so well known facts about the solar system. I'm hoping that most of these will be a surprise to most of you, but for those who get to the end and are not surprised by everything, I've got a slightly longer title for you, and that is Solar System Stuff You Already Knew, but is really cool nevertheless. So I should point out that if you do know that, if that's one of you, then you have to quote that title at the end. And you also have to list all the dwarf planets in the talk in alphabetical order. No, I'm just kidding. Any order will be fine. So does anybody, no, only show of hands, don't call it out, no spoilers. Anyone know what that is? It's not a comet, and it's further away than the moon. Someone does? Okay, we have one person. You might be the person to be reading out the title at the end. But that's all right, I won't do that to you. And so that's one of the things we're going to look at tonight. Now I'm going to start with an overview of the solar system, mainly a bit of a tour of the solar system and where it sits within our galaxy. And then we're going to head out to where it's really cold and really dark and have a look at Pluto and some weirdly named objects called plutinos, twotinos and Q-B-waanos. I haven't made any of those up, they're all real. Then I want to have a look at tails and rings. So you're probably aware, of course, that comets have got tails. We've just seen something before that's not a comet that has a tail, so we'll find out what that is later on. And you might also know that the giant planets have rings, and I'm going to show you 4 other things that have rings in the solar system as well. And then finally, we're going to come back closer to home and have a look at Venus, something called Zeus V, some of you might have heard of that, and Earth's other moons, which is quite topical at the moment. So first up, where is our solar system? And a bit of a quick tour. So that is our galaxy, the Milky Way. Now that's an artist's impression because we can't go that far out of the galaxy to take a photo. It would take hundreds of thousands of years to get out there. But it's probably pretty close to what a galaxy would look like if we were out in space. And that yellow arrow there shows where we are within the galaxy, about 26,000 light years from the centre. Now I've zoomed into a single pixel here of the image, and I'll divide that into 1 billion by 1 billion squares. And if we take one of those billion squares, our sun would fit into that square. So that's in a billionth of a pixel is where our star would fit. So you can see it's a very big galaxy, even though it's an average sized galaxy. There's about 350 to maybe 400 billion stars in our galaxy, our sun being one of these. Now our solar system consists of, I better get out of the way of that, we'll stand over here, of one star called the Sun or Sol, and that's why the whole thing is called the solar system. We have 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. The little inset up the top there just shows the sizes of the small planets compared to the large ones. Now while we're looking at this, the distance between the Sun and the Earth is about 149.5 million kilometres, but in astronomy we can just call this one astronomical unit, which makes it a lot easier to talk about distances in the solar system. So you don't need to remember all those numbers or all the numbers for the other planets. Just remember 1 AU, which means that Mercury is about 0.4 of an AU from the Sun, Venus about 0.7, Mars about 1.5, Jupiter about 5, all the way out to Neptune, which is 30 astronomical units roughly from the Sun. There are 6 confirmed dwarf planets. I won't get in the way of those. 6 confirmed dwarf planets. Ceres in the asteroid belt over here. Pluto, Makemake, Haumea, Q-B-waanos, it's a hard one, and Eris, and another 5 at least candidate dwarf planets: Gong, Orcus, Ixion, Sedna, and Salacia. Q-B-waanos, some of you might kind of know that that's a bit on the edge as to whether it's a dwarf planet or not, but it is tonight for our talk. Now these are the sizes of Pluto, Ceres and Eris compared to Earth, just to give you an idea how small dwarf planets are. The size of Eris on the right, that's the largest dwarf planet of them all. So you can see they really are very small objects. There are over 300 moons in the solar system around planets and dwarf planets. Saturn has a count of 146 moons at the moment. Now only about 7 of those are actually spherical, the rest of them are kind of irregular shaped asteroid type things. Jupiter, 95 moons. And then we have 5 around Pluto and a few around the dwarf planets. At least 1.3 million asteroids. Some of those have their own moons as well. And the asteroid names are, no, we won't go through those, 1.3 million of those. Possibly millions of Kuiper Belt objects. The Kuiper Belt is a region of the solar system from Neptune's orbit out to about 55 astronomical units from the Sun. Now that's filled with icy, rocky, comet-like objects. All of the dwarf planets, in fact, are Kuiper Belt objects except for Ceres. So all those ones outwards, Pluto onwards, are Kuiper Belt objects. There are 4,000 or more comets in the solar system, and many of these actually come from the Kuiper Belt itself. Some come from further out, and we'll have a look where that is. So if we zoom out, we can get a better idea of the Kuiper Belt, which is actually more of a donut shape, so the picture doesn't really show that so well. It's more of a donut shape than a disk. And it contains, being a Kuiper Belt, the objects are called Kuiper Belt objects, so nothing too exciting about that, or KBOs for short. So instead of saying Kuiper Belt objects all the time, you can just say KBOs. And even further out is this gigantic spherical cloud of more rocky, icy objects called the Oort cloud. Now that may extend much further than it even shows in that image there. It could extend out to a light year from where we're sitting, which is in the middle. You can see that little tiny dot there, the purple one there, which shows the Kuiper Belt and the Sun. And even then it's probably drawn a little bit large. So if the Oort cloud goes out to a light year, that's almost a quarter of a way to the nearest star. So it's a very large region. And the reason it's hypothesized is because of certain comets that come from a long distance away from us. Now, in sci-fi movies, you'll probably see asteroid belts seem to be somewhat crowded, like the image up at the top there. In reality, it's more like this. If you saw one asteroid, you might just be lucky enough to see another one reflecting sunlight in the distance. The average distance between the asteroids and the asteroid belt is about 1 million kilometres. In the Kuiper Belt, the average distance between objects could be 100 million kilometres. So it's a very big region of space, but there's a lot of room for a lot of objects out there. And the age of our solar system is 4,568,400,000 years, plus or minus 200,000 years. And that's calculated from meteorites, which I think Joel might be talking about next month, and you may learn a bit about how we work that out next month. So now we're going to move on to the dark, cold part of the solar system. So we'll look at Pluto and plutinos, twotinos and Q-B-waanos. And while we're there, we might as well have a look at why Pluto is not a planet anymore. So I'll start with that last question first. In 2006, the International Astronomical Union came up with 3 criteria for defining a planet in our solar system. Now, the first one is that a planet must be orbiting the Sun. So I've used Mercury as an example in this case because Mercury is now the smallest planet since Pluto is no longer a planet. Pluto is still in the solar system. I've had some people say, oh, is it still in the solar system or is it gone somewhere? But it's still in the solar system. It's orbiting the Sun. And so Mercury and Pluto both passed that orbiting the Sun test. As well as that, it has to have enough mass to pull itself into a spherical shape. And as we can see, Pluto and Mercury both passed that test as well. If it didn't have enough mass, it could be irregularly shaped and it wouldn't be able to squash itself any further. But finally, to be a planet, an object has to have cleared its local neighbourhood of debris, of other rocks and icy bits and pieces in its orbit. So that really means that gravity of the object could fling other objects away. So let's say something large, if it was Pluto, but Pluto obviously doesn't, but if some large object comes along and meets an asteroid, the asteroid might be pulled towards the large object and then go around it and flung out into space, and eventually it would clear its orbit. But sadly, Pluto has not cleared its orbit, and so it actually fails the planet test. Mercury, as you can see, has passed the planet test, but at least Pluto has passed the dwarf planet test. Now, so we need all three for a planet and 1 and 2 for a dwarf planet. To be fair, you kind of wonder if Mercury had a lot of objects in its orbit, whether it would have cleared them out as well. So I suppose Mercury's just kind of lucky that there's nothing else there, so we just call it a planet. But I'm not sure if it would actually have passed had there been a lot of other objects in its orbit with it. Now, one fun fact about Pluto is that it was the only planet discovered from the United States. And so that was a little bit unfortunate. But at least it was the first Kuiper Belt object, KBO, that was discovered. So it's got that going for it. Now, if we look at Neptune's orbit, and then go out to 55 astronomical units from there, we find the Kuiper Belt, as we mentioned before. And so that far end of the Kuiper Belt's about 8 billion kilometres from the Sun. Now that, as I mentioned, consists of these rocky, icy objects called Kuiper Belt objects. Now Pluto is a KBO. Pluto's inclination, which is the angle it orbits compared to Earth's orbit. So Earth orbits in what we call the ecliptic. Pluto is at an angle of about 17 degrees, so it's quite an inclined orbit. The other planets, or the planets, have little inclinations here and there, but 17 is quite high. As well as that, Pluto sometimes comes within the orbit of Neptune, and most of the time it spends outside the orbit of Neptune. So it does cross Neptune's path, but it doesn't ever crash into Neptune, so it's pretty safe. And the reason for that is this other very interesting thing about Pluto's orbit. Pluto is in what we call a 2-3 orbital resonance with Neptune. And that means for every 2 orbits around the Sun that Pluto does, Neptune does 3. So if you can do that with your hand, do 2 and then 3 and get that exactly right. You can practice that and get it right by the end. So that's a 2-3 orbital resonance, and what it means is that Pluto will never actually get in Neptune's way and will never crash or be thrown out of the solar system. So here's a bit of an animation just to give you a bit of an idea what's happening. These vertical lines up here just show how far Pluto is above or below the plane of the ecliptic. So you can see that as Pluto and Neptune go around, we're ending up with this kind of 2-3 orbital resonance. And if I just pause it, we can see Neptune starting here, Pluto starting over here, getting them moving. And if we watch right around for one of Pluto's orbits, we'll see that Neptune will have been around 1.5 times. So we'll just let that go around. You can see here's Neptune coming around, finishing 1. Pluto's coming around, just about finished its first 1. And once we get to this point, we can stop it there. We can see that Pluto's back to the start. Neptune's done 1.5 orbits. So of course, 1 more of these cycles, and we'll have 3 for Neptune, 3 for Neptune, yes, and 2 for Pluto. Now, about 1/4 of all the KBOs actually share that resonance with Pluto. So it's not just Pluto that has this 2-3 resonance. And so those objects in this 2-3 resonance are called plutinos, after Pluto. And here's a couple of other ones here. This one's Orcus, and here's a little video up here. It's actually a few frames of photos of Orcus. And Orcus has a little moon orbiting it called Vanth. Over here is Ixion. That's another dwarf planet candidate. And Ixion doesn't have a moon, but there's an image of it as well. So those are the best images we can get of these objects. They're so far away and so small. So we've seen the plutinos. They're in this 2-3 resonance. But there are some objects that are also in a resonance in a 1-2 resonance with Neptune. And these are called twotinos because of the 2. So there are about 100 twotinos or so known to date. And there's 2 of them over there. The names, I'll explain those at the end. The date, of course, is the year discovered, but the other numbers mean something as well. So that's the names these have been given. They haven't been given a final name. They're obviously not important enough to be given an exciting name. But if you look closely, you can also see next to those photos, very little dots beside them. And again, those are little moons orbiting them as well. So there are a lot of moons, a lot of small objects orbiting larger objects in the solar system. I think it's really quite amazing that we can see these images of these things so far away that are so small, and then see that they've got moons going around them as well. They would have been Hubble, I think. Yeah, I'm pretty sure that was Hubble. There's also a group of objects called the Neptune Trojans. Now these orbit in a 1-to-1 resonance with Neptune. So a year of Neptune is the same as a year for each of these Neptune Trojans. Down to the bottom you can see that is the first one that was discovered in 2008. So there's a few of the discovery images that you can kind of see an object that's changed position in between each of the photographs. You can see that it's not easy to find these things, so it takes a lot of work to go through these photographs and a few other ones as well and work out exactly the direction and the speed and work out what it's related to. There are 31 Neptune Trojans known of at the moment. 27 of those orbit in front of Neptune and the other 4 are behind it, and they're about 60 degrees ahead and behind Neptune in the orbit. Those are the Neptune Trojans. But there are also more, so there's the 3-4 resonance, so 4 for Neptune and 3 for these objects. There's not enough of those, there's about 30, so they don't get their own special name. And then a whole lot more as well. So we've got the 1-4s, the 1-5s, and a whole lot more, including all these weird kind of resonances. So I think it's pretty cool actually to think that we've found these objects, worked out what they're doing, and that they have these almost exact number of orbits with Neptune. This one here, 712, is the resonance of Haumea. That's one of the dwarf planets we looked at the start. Now with those ones not having proper names, I guess if you wanted to call the 1-4, you'd probably call it a 4-tino based on that 2-tino, and maybe the 5 would be a 5-tino. No one's come up with names, but I'm sure someone could. And I don't know what you'd call those, but based on plutinos, that would probably have to be a Haumino. So if you're bored sometime and you want to come up with some names for these groups of objects, have a bit of fun, I think. Now, the question, I suppose, is what causes these resonances? And really what happens is that Neptune shepherds these into these resonances. So any objects that don't cooperate with this are flung away or captured. And in fact, quite a few of Neptune's moons will actually be captured Kuiper Belt objects. That's Triton over on the right-hand side there, Neptune's largest moon. So that's the scale, size, and distance-wise. Triton is almost certainly a captured Kuiper Belt object. If we have a close-up look. Now that's expected to be a captured Kuiper Belt object because it's orbiting Neptune in the opposite direction to which Neptune is rotating. So if it had formed with Neptune, you'd expect Neptune to be rotating a particular way and the moon to be going around with it. That's called a prograde orbit. But that's in a retrograde orbit, so pretty certain that it's been captured. Triton's just a little bit larger than Pluto. They're actually very similar objects. That's Pluto's largest moon, Charon, which is actually a lot further away, but I couldn't fit it on the screen, so I just brought it in closer. Now, it's quite possible, or quite likely even, that Triton had its own large moon as well before it was captured. The reason that is most likely is because it would aid in the capture process of Triton by Neptune. What would happen is Triton with its moon would come along, get close to Neptune. There'd be a few things happening physics-wise, and Triton would lose a bit of energy, a bit of speed, but its moon would gain that energy, get extra speed and be flung out of the system, and then Triton would have a low enough energy to stay bound to Neptune, and that's why it's pretty likely that Neptune had a large moon when it was captured. There's other possibilities as well, but that's probably the most likely one. So what then are Q-B-waanos? Well, Pluto was the first Kuiper Belt object discovered. The next one discovered was in 1992, and that was called 1992 Q-B-1. Now, these are some of the first images again, so you can see a few pictures to kind of show something's moving and then eventually work out what's going on. So those are the first images of Q-B-1. It's actually now got a final name, it's called Albion, but originally it was called Q-B-1. And like most objects in the Kuiper Belt, Q-B-1 is very small, about 100 kilometres by about 170 kilometres, so a very small object, very far away from us. Now, this object has a fairly circular orbit, and it actually keeps away from Neptune quite nicely, and so it doesn't get controlled by Neptune, and so what that means is that it doesn't need to be in any particular resonance, so it's pretty safe, just orbiting out there at its own speed. Now that means that not being controlled by Neptune, that it's almost like a classical planet, so that'll become clear in a moment why we kind of think of that as a classical object. So Q-B-1 was found, and then after time a few more of these same kind of objects in similar orbits were found. There was one called, this is Q-Wa that we saw earlier. There was one called Chaos, because you've got to use the word chaos if you can use it somewhere, and that's where it's been used in our solar system, because it's such a neat name to use. There's one called Varuna, and then another one found called Makemake. Now Makemake is actually on quite a high incline on its orbit. It's about 29 degrees, so each of those little angles shows the inclination of these objects. So these objects, and a few more discovered, so there are only some of them, these became known as the Q-B-waanos, and you might be able to see that's a play on the words Q-B-1. So they called these objects all Q-B-waanos. Later on, these have kind of become known more as the classical Kuiper Belt objects. Classical because you can kind of see, it looks like they kind of orbit more like the classical planets, even though some of them are dwarf planets, but some of them are just smaller things with no real shape to them. They actually divide these into two categories as well. They're called, we have hot classical objects and cold classical objects. Nothing to do with the temperature at all, but if something has an orbit of more than 5 degrees inclination, they call it a hot classical object, and if it's less than 5 degrees, it's called a cold classical object. So now our Kuiper Belt has our resonant objects, our hot classical objects, and our cold classical objects. There are other ones as well. There's something called the detached disk and or detached objects and scattered objects as well. So there's quite a few different types of groups of objects out there. And really there's a lot more to the Kuiper Belt than we can cover in this talk, and it really deserves its own talk sometime, probably even 2 talks. There's so much happening out there. And now that 30 to 55 astronomical unit area is probably really better described as the main or the inner Kuiper Belt, because as I mentioned, there's so much more out further than what we just saw there. So just before we head on to the next topic, just show you some of these. There's Pluto, a couple of other plutinos. There's a couple of the twotinos for you in green. Some of the 3-4, or one of the 3-4 objects there, and that blue is Neptune's orbit. And some Q-B-waanos thrown in for you. Then put them all together, and there's a very small number of our Kuiper Belt objects. And over to the right here is just a bit of a diagram showing from the side so that you can see the inclination. Earth is kind of in the flat in the middle there. So now we're going to look at tails and rings. So that is a tail with rings. That's actually something called a ringtail, not a ringtail lemur, but a ringtail or even a ringtail cat, although it's not even a cat. So it's just as bad as astronomy when you get into the biology type of things. So anyway, we're going to look at rings and tails separately. So as I mentioned before, we all probably know that comets have tails. And here are some photos of comets. Over on the right-hand side, Neowise, Hale-Bopp and West. And those three in particular, if you look at the tails, you can notice something a little bit unusual, which I'll come back to later. So as an aside, there are two ways, or a couple of ways to categorise comets, but one way is by the number of years they take to orbit the Sun. So a short period comet is a comet that takes less than 200 years to go around the Sun once, and they are objects that originate in the Kuiper belt. Then we have the long period comets, which have a period of more than 200 years, which originate in the Oort cloud. In fact, that's why the Oort cloud is thought to be there, because of these comets with the long periods. And then there are interstellar comets, comets that come and visit us from outside the solar system, come by once and continue out, too much energy to be captured, except sometimes it's possible, we don't know of any definite ones, but it'd be possible from simulations for them to come close to Jupiter, get deflected and then get kind of slowed down and remain in our solar system. But Comet Borisov is the only truly confirmed interstellar comet that we've seen. It was found in 2019 and was travelling at 177,000 kilometres per hour. So it was going pretty fast. And by a very convenient coincidence, there's a comet around at the moment that's called Shushan Atlas. And that's a photo there taken by Alex. Where's Alex? Over there. Well done. So that photo was taken by Alex. So that's Shushan Atlas. Now this comet, it's been worked out as probably has an 80,000 year period, which means it'll be a long period comet that's come to us from the Oort cloud. Now, up here on the left-hand side is a little animation showing the comet coming around the solar system past Mercury is the green one in the middle. Apparently from about the 12th of October onwards, we should be able to see it quite well in the sky, but I think that might be only if you're in the northern hemisphere. Unless it breaks up as it goes past the sun, it has a possibility of disintegrating. Oh?
It should be visible from here.
From here as well? Oh, so that's even better.
Just up, I was looking at the 18th,
Oh, cool.
bottom of that below this.
Yeah, oh, there you go. That's actually really good. So we might actually get to see it at that stage. So hopefully it won't disintegrate. I don't think there's any sign of it disintegrating at the moment, so we should be pretty safe. And this other, I'll move out of the way there. This other one here is just another little picture of the orbit of the comet, just showing how inclined it is compared to the planet. So it's an inclination of 139 degrees, which is actually right past the 90, and it's going in a retrograde direction compared to the planets. That little diagram also gives a nice view of Mercury, which is actually quite inclined too compared to the other planets in the solar system. Might as well admire Alex's photo there for a minute. Now, a comet is made up of rock and dust and ices, and the ices include frozen carbon dioxide, ammonia, methane, water, various other ices as well. Now, when a comet gets close enough to the sun within, say, 5 or 6 astronomical units, which is 5 or 6 times the Earth-Sun distance, it's warm enough for those ices to vaporize and produce a kind of an atmosphere called a coma. And the coma can be up to tens of thousands of kilometres across, so it can be pretty big. So probably a lot bigger than what that picture shows there. And this coma gets blown away blown outwards by the solar wind as well as radiation pressure. Radiation pressure is just the pressure from light itself. So light actually does have a pressure. And this forms the tail. Now the tail points directly away from the sun. It doesn't point behind the comet, where the comet came from. It points directly away from the sun, at least to start with. So if we have a look at a bit of a diagram here, we can see that comets have two tails. The two tails are an ion tail, which is the gases, so the ice as it vaporizes produces gases. The ion tail will continue to point away from the sun. That is pushed out by the solar winds and the particles from the sun. So as it goes around the sun, that's always going to point away from the sun. The second tail is the dust tail. The dust tail doesn't get affected by the solar wind, but it does get affected by the light pressure. So it starts off pointing away from the sun, and then it does curve a little bit backwards from where the comet came from. And I think that Neowise one is a great picture to kind of show those two tails. The ion tail is blue in this case because of carbon monoxide. So carbon monoxide, when it's lost one electron, becomes ionized, and that scatters the blue light. So we have a blue ion tail. And the dust tail is made of tiny particles, about a micron, about a millionth of a metre in size, a bit like I think cigarette smoke is what is described as probably the most similar kind of size particles in the dust tail. So this is that picture we saw at the start. So now, Alex, I think you might have an idea. Can you tell us?
Mercury.
Mercury, very good. So that's Mercury with its sodium tail. Now, the tail of Mercury is about 24 million kilometres long. We can't see it with our naked eye. We have to have a special filter, so it's a sodium filter, and that's why it's kind of orange in this picture here. The same as the orange of those old sodium streetlights we used to see around. I don't know if we see many of those now, but the sodium streetlights had that same colour. It was 589 nanometres. So it's pretty amazing to think that Mercury has this tail, always points away from the sun, blown out by the solar wind. So the question, I suppose, is where does that gas come from? Well, Mercury has what we call an exosphere, which is a very tenuous atmosphere produced by a process, one process called sputtering, where the solar winds come down and knock atoms or molecules out of the soil into the atmosphere, as well as micrometeorites, very small meteorites that come down and shock and vaporize. And I suppose if you were hit by meteorites, you'd probably be shocked too, so I think that's quite good wording. So it shocks those out into the atmosphere. An exosphere is like an atmosphere where the particles are so far apart that they don't collide. So in our atmosphere, the atoms and the molecules in the air collide together. But these particles are so far apart, we call it an exosphere. And then these particles get again blown away by the solar wind, not too different to a comet, and produce that amazing 24 million kilometre tail. And this is the moon with its sodium tail. So the moon has a sodium tail produced pretty much the same way as Mercury's sodium tail. Not to such a large extent though. This tail is only about 800,000 kilometres long. I say only, which is still pretty big, but just not as big as Mercury's one. Again, we can't see that with the naked eye, and it's almost even harder to see with special equipment than Mercury's tail. So this is an animation, that was an animation from a simulation. And again, the particles are knocked off the surface of the moon in the same way from the solar radiation. So if we just kind of look at a couple of frames, you can see that Earth does pass through that tail occasionally when it lines up correctly. And Earth's gravity can kind of focus the tail behind a little bit, so we have kind of a more dense tail for a short time. The pictures up the top and right kind of show what the view would look like from Earth if you had good enough eyes to see the particles. So it gives you an idea, that top right one, what we'd see.
Do you think that us amateur astrophotographers could get that?
I've seen a couple of the science photos of that, and it's very hard to make out what you're looking at. So maybe a bit of research, you might be able to find a way. Mercury could probably, with the filters, find a get a photo of that.
The moon, of course, is the moon itself is right. That you've got to do it, and you're probably near new moon, and then you're getting into twilight.
That's right, yeah. So there's a few problems to do that. So you're right, yeah. So it'd be a tricky one. It'd be worth interesting to have a go though, see what you could do.
But wouldn't it be easier to see if it was first quarter? Because then you're looking side on.
Yeah, I guess, yeah.
The tail behind the moon, you mean?
Yeah. So kind of out to the side. I think because it's so tenuous, it's probably going to be quite hard. But no, definitely, yeah. If you can have a go, that'd be really cool.
Can the sodium be detected on Earth?
If we're actually landing on. Actually, that's a good question. I'm not sure. I know that they can see it, and it kind of looks like that spot. Kind of looks like a spot on the moon, just like optical illusion. But I imagine if it hits the atmosphere, a bit of it must come kind of raining down. So we probably should be able to, shouldn't we? That's a good question, though. I hadn't thought of that.
Well, just if you're on a low sodium diet, you might have
Yeah. Actually, it could interfere with that a bit, couldn't it? Yeah. So we'll have to watch out for that on those certain times when we pass through the tail. So let's have a look at rings. We know that there are 4 planets in the solar system with rings. And I suppose if you didn't know that, there's a surprise for you. So the 4 giant planets have rings. Saturn, which we know about. Jupiter's rings, which were discovered in 1979 by Voyager spacecraft when it went out around the other side. The rings are very thin and very transparent, so it was kind of going around the other side of Jupiter with the light coming through, and probably a bit of help from infrared as well. So these 2 are photos. The 2 on the right, Neptune and Uranus, are artist impressions because those rings are very dark and very hard to see. There are some nice pictures online of these rings in infrared, which are pretty cool to have a look at, so I'd encourage you to have a look online at those. So here's our solar system with our planets and Pluto out to the side here. And the first object we're going to have a look at with rings is dwarf planet Q-B-waanos. So Q-B-waanos has 2 sets of rings. Then we have Haumea. Haumea is a kind of an egg-shaped dwarf planet. As I mentioned earlier, that dwarf planets are meant to be almost spherical in shape. That's egg-shaped because it's probably one of the fastest spinning objects in the solar system, and a day on Haumea is only 4 hours. So it's a very fast spinning object, and it has 1 ring around it. Those are the orbits of Haumea and Q-B-waanos out beyond Pluto. Well, Haumea is within Pluto just, and Q-B-waanos a little bit as well, but out beyond Neptune. Then we have asteroid Chiron, which has a triple ring system. Now that's actually better known as what we call a centaur, which is a half comet, half asteroid, so quite a bit of ice and rock as well. And finally, we have asteroid or centaur Chariklo, which has a double ring system around it. And these 2 objects orbit in between Jupiter and Neptune are very small, so we'll have a look at the size of those now. So you can see that these pictures are not to scale, that these are very small objects. Q-B-waanos about 1,000 kilometres across, compared to Haumea, which is about twice the size, 2,000 kilometres or so. And the ring distances I've just shown in there as well to give an idea of how far the rings are away from these objects. Now Q-B-waanos rings are a little bit strange because there's something called the Roche limit. Now you may or may not have heard the Roche limit, but within this thing called the Roche limit, generally tidal forces will break objects apart. And so rings would usually be within this Roche limit. Outside the Roche limit, you wouldn't really find objects being broken apart. So the fact that there's rings outside the Roche limit around this object, Q-B-waanos, is a little bit unusual and a bit of a mystery at the moment. Looking down here at Chariklo and Chiron, we can see these are only about 300 kilometres across. They're very small objects. The rings around Chiron, when they were first discovered, 3 were seen, and then on the next go at trying to see what was there, they only saw 2. So it's quite possible that this is more some sort of evolving disk of debris around Chiron. Now let's have a look at some photos. So here's Q-B-waanos with its little moon Waywat, and Waywat is way up further than the rings. And Haumea with its two moons, Hi'iaka and Namaka. These little moons are about 25,000 and 50,000 kilometres away from Haumea. And again, these are the best photos you can get of these very small, very distant objects. And Chiron and Caraclo. So one thing you might notice is that these artist impressions show these rings around these objects, but the photos don't show any sign of any rings. So you might be wondering how on earth we can know there are rings around these. Well, here's a little animation I've just made just to kind of give you an idea of how we can find these rings. So if we pretend we've taken a photo of some distant object up here, and we've taken a whole lot of photos, string them together and make a little movie, and then kind of watch each frame, you'll kind of see something happening with some of the stars behind it. And you might notice the dimming of stars. And from this you can tell that this fictitious object has two rings around it. Not completely... I
presume the dimming in this animation is highly exaggerated.
It is. This is a very, very exaggerated picture, so you can get an idea of what's happening. So if I exaggerate even more and show the rings, you can see that, you can kind of see what's happening there. Yes, in real life, it's much, much harder. This is called stellar occultation, where it just slightly dims the stars or slightly hides the stars behind them. Here's another animation which is probably a bit more realistic, but even this is probably not as hard as real life. So if you have a look at that little dot up there with the arrow and just watch that kind of going through, you wouldn't even have that many frames. So this is way, way exaggerated. And don't worry if you can't see what's happening, it's meant to be hard just to show you how difficult it is. So that's not a real object there, but down on the bottom left-hand side there is data from Chiron. And you can see from Chiron that there are three rings here, where a star behind it has been dimmed as it goes past a little bit, then dimmed again a bit more, and then dimmed a lot more. So you can see three sets of rings with a lot denser ring closer into Chiron. And so you can hardly even see that happening, but as I mentioned, that's actually still easier than the real thing. So one question is, did Earth ever have rings? I would have thought no, until a little while ago, where some research was done looking at craters around the world that had been formed about 466 million years ago. Now these craters seem to be dotted around the world. There's about 20 used in this study, but by looking at the craters and running plate tectonics backwards, it appeared that they were all kind of roughly around the equator of the Earth at the time that they were formed, which would almost point to something collapsing, a ring system collapsing around the Earth, creating these craters at the same time. So that would have been 400 to 500 million years ago. So that's kind of a new thing that I've just learnt about. It probably wouldn't have been quite as big a clear rocks as these orbiting the Earth, but it's possible Earth may have had a ring. It would have just been a broken up asteroid that probably got caught very close to the Earth, and the debris from that would have given us the ring. Another example, Saturn's moon Iapetus. Now this is one of Saturn's moons. It's one of the Death Star type moons. Mimas and Iapetus kind of have that little, I think you can almost see the Death Star kind of look there. Iapetus has this mountain range around the equator. There's a close-up view of it there, which may be, or may not be, the remains of a collapsed ring as well, being right around the equator. So that's another bit of research people are looking into. If it did have a ring and Iapetus was captured by Saturn, it probably had its ring before it was captured. I can't really imagine a ring existing around a moon as it was orbiting a planet, because I think the tidal forces would probably put it away, but it's quite possible that object had a ring as well. So Back closer to home now, we're going to have a look at Venus, Zeus V. So Zeus V is a temporary quasi-moon of Venus. I'll explain what that is in a moment. And then Earth's other moons, quasi-moons, and something called a mini-moon, which has been in the news recently. This is the surface of Venus taken by the Soviet Venera 13 lander in 1982. The lander only lasted about 2 hours before it melted. And you'd probably struggle there as well because the temperature on the surface is over 460 degrees Celsius, so well over 440 degrees what we feel in here at the moment. And the pressure is about 93 atmospheres, so about 93 times the pressure that we feel right now. That would be the same as being a kilometre under the water. So it's incredibly horrible conditions there, the temperatures and the pressures. But apart from that, if you look at the atmosphere, that's 96% carbon dioxide compared to Earth's 0.04, so quite a greenhouse effect there going on. 3% nitrogen, as well as some sulfur dioxide, carbon monoxide, and some other nasty bits and pieces as well. And just to make it a bit worse, sulfuric acid clouds. So it's a great place not to be. You wouldn't want to live there. That's an artist's impression, by the way. Now, interestingly enough, between about 48 or about 50 to 60 kilometres above the surface, it turns out that the temperature is a nice cool 30 to 70 degrees Celsius. Not for us, but maybe for microbes. And the temperature and the pressure is close to 1 bar, so what we're kind of feeling here. So there are extremophile organisms on Earth that would love those conditions. And there are actually some extremophiles on Earth that happily eat sulfuric acid as well. So it's not impossible to think that if we took some of our microbes and put them into the atmosphere there and they kind of floated around, they might live happily in the atmosphere. As well as that, a molecule called phosphine, not phosphate, was discovered twice in the atmosphere of Venus. Once in 2020, but it was kind of discarded because it couldn't be repeated again, so it was thought that was just some misreading. But then again in 2023 it was found again. And the interesting thing is that phosphine on Earth in large numbers needs a biological process to form. So it's kind of interesting that that should be sitting in the clouds at about between 55 and 80 kilometres above the surface. When you put that together with what we saw before, the phosphine and the nice temperatures and pressures, there's a little bit of an overlap there. So all I can say is we don't know, maybe. But phosphine might have some sort of other non-biological way of being produced. So who knows? We'll have to go there and have a look and find out. But it's something to think about and get excited about, maybe. Okay, back out into space again. There's an asteroid called 2002 VE68 that orbits the Sun with the same year as Venus. And so it's in a 1-to-1 resonance, mean motion resonance with Venus. This object, Zeus V, was, well, I should say 2002 VE, is now called Zeus V because an artist apparently wrote down 2002 VE in his notes, came back to it later on and couldn't read his handwriting and thought he'd written Z-O-O-Z. And so he thought, oh, this is Zeus V. And then that became known as the name for the object, so its final name ended up being Zeus V. A bit like Q-B-waanos is now Albion, 2002 VE is now Zeus V. So this object, Zeus V, orbits the Sun, and you might notice from the animation that because it goes around the Sun at with the same year as Venus, it's always kind of nearby Venus. So it's not orbiting Venus, but it's always nearby. So if you were on Venus looking out, it would look as if it was orbiting Venus in this weird kind of kidney-shaped orbit. And that's called a quasi-moon, so it's not orbiting Venus, but it kind of, the illusion is that it's orbiting Venus, and so that's Venus's quasi-moon.
Does the Earth disrupt its orbit to some degree because it looks like is it in the same plane?
Interesting, Our models show that it's probably been there about 7,000 years, and it will probably be ejected in about 500. So I guess Earth's interference with it will probably, and Venus and maybe a bit of Mercury, will probably eventually knock it out so that it shoots off somewhere else. It won't be exactly in the same plane, but yeah, it will be getting close enough to the other planets to little tiny movements and little tiny changes. That's pretty cool. Venus and Mercury can't have their own moons orbiting them. They're too close to the sun. So if Venus had a moon, as it got around the sun side, it would get tugged a little bit each time and would eventually lose its moon. So there's a close-up view. But Earth also has quasi-moons. In fact, we have 7 quasi-moons. This is the orbit of one called Camo-Aleva. And again, we've kind of got the camera over Earth, so to speak, in this animation. So looking at it from Earth, we can see it's actually orbiting the Sun with the same year as Earth, 365.25 days. But because it's always close enough to Earth that from Earth's point of view, you could almost look at it and think, oh, that looks like it's orbiting Earth. But it's not in the same plane, and it's kind of a bit messy. But that's probably, they think, it's probably a piece of our own moon that was knocked out by an asteroid that hit the moon. I think it's only a few hundred meters across. It's not that big. And here are the other 7. We won't look at all of them, but just out of interest, 2004 GU9. Similar kind of thing. It's orbiting the Sun with the same year as the Earth, kind of near the Earth. And if we look at it from the point of view of Earth, that gives a really interesting kind of orbit. A bit of a clue from anyone on Earth looking at it that it's not orbiting Earth, because nothing could orbit like that. But it's always close enough to Earth that if you just looked at it, you'd draw that kind of orbit. Well, illusory orbit. So we have 7 of those quasi-moons.
Do you think they're bright enough for us to image?
That's another good question too. I think that they might be big enough at the right time to look at. The next things we're going to have a look at in a moment are mini-moons, which are be way too small, but these will be a bit bigger, so you might just be lucky enough to, yeah, depending on your size of the equipment. And again, I'd be interested to see if you do, if you can. Yeah, it looks like we might have a bit of a talk with some good images of things if you can get some for us.
Well, Alex has access to a 16-inch now.
Oh, okay, there you go. So let's have a look at that sometime. So let's have a look at mini-moons now. Mini-moons are temporarily captured asteroids. So they come in close to Earth with too much energy to be permanently captured, but the interplay of the gravity between the Earth and the Sun means that they can kind of hang around for a bit, but eventually the Sun's gravity will just perturb them enough that they'll end up shooting away. This one lasted, well, it was seen in 2020, or 2019 I should say, and it's thought that it was probably captured 2016, 2017, and we know it did escape in May 2020. It's called a long capture because it had quite a few orbits around the Earth in that time. That was a very small object, that was less than 3 meters, and I think that would be pretty hard to see with any telescope other than a very large professional telescope. And that one is called 2020 CD3. I guess it was really officially recognised in 2020. And by another convenient coincidence, we have one of these just around us at the moment. This one is 2024 PT5. This one's about 10 metres in size, so it's a bit bigger. This is a short capture, so it doesn't even really orbit the Earth once. We'll have a look at it from a different angle in a minute. This was officially captured, weirdly enough, over here, and will officially be released over here. So you can see while it's officially a mini-moon, it's not even orbiting the Earth. The reason that it's officially captured is that its kinetic energy or speed compared to the Earth around there is lower than its potential energy compared with the Earth. So it's kind of called temporarily captured. For the rest of the time, it's going too fast and it's really just being deflected by the Earth. And if you look at our animation here, you can see from a different angle that it doesn't even look like it goes around the Earth. It comes up here. The gravity from the sun and the Earth are kind of pulling it in different directions. Now it's coming back towards the Earth. Now the sun's gravity is kind of pulling it out in a different direction. Coming back up again, trying to get back, but then will escape. So that's our current mini-moon. It's hanging around at the moment. It's kind of almost pushing it to call it a mini-moon, that one. I think the other one, 2020 CD3, is much more moon-like than that one. So the Shushenshan comet that we saw before was discovered by ATLAS, which is the Asteroid Terrestrial Impact Last Alert System. Interestingly enough, that ATLAS was also what found this object as well. So just to finish off with, I think it's worth just having a look at what these names mean, because they've kind of been throughout the talk, these kind of strange names. So we'll start with Mini-Moon 2024 PT5. The green, or the year, is the year of discovery, so this was discovered in 2024. The P means the half month that it was found in, so I'll get out of the way again there. The half month, A is the first half of January, B is the second half of January. So Mini-Moon PT5 was discovered in the first half of August 2024. Now the T5, or the last two digits or characters, tell us the order of discovery. So the first object discovered would just be A, so we'd have 2024 PA. The second object would be B, get to Z, and then you start adding numbers. So T5 means the T is 19, because it's not the 19th letter, but it would be if you get rid of I, because they don't use I, because it might get confused with 1. So the T means 19, the 5 means 5 times 25, because they do it in groups of 25. So just take 19 plus 5 times 25 means it's the 144th object, non-cometary object, discovered in the first half of August 2024. So that's the code. Comets have a slightly different code, so you might have noticed that a comet before was 2023 A3. So that was discovered in 2023 in the first half of January, but they don't worry about the letters there because obviously not enough comets to be discovered. So it was the third comet discovered in that half month. So see, the last one to have a look at is Zeus V. So now you know that's 2002 it was discovered in. V means it was the first half of November. And E68 means it was the 1705th non-cometary object discovered then. Obviously a lot of things were being discovered around that time. And so that's the meaning of those codes. When they discover new satellites around planets as well, they have a slightly different code as well. But you'll see, as you saw through the talk, there are a lot of those codes, so I thought it was probably worthwhile just showing you what that means. So that kind of brings us near the end, so I'll just quickly take us through a summary. Solar system, 26,000 light years from the centre of the galaxy, 4.568 billion years old. We saw Pluto and its friends out there in orbital resonances with Neptune and the Q-B-waanos, named after Q-B-1. We saw that Mercury and our moon both have sodium tails. I didn't mention there's a couple of other tails. Sometimes Earth develops a short tail, and Venus, you can Google these, and also Saturn's moon Titan develops a short tail when it comes outside the magnetosheath, I think, and it gets blown towards Saturn, so it's out of protection of Saturn's magnetosphere. And then we had a look at the possibly habitable region of Venus, some quasi-moons and some mini-moons. So that brings us to the end of the talk. Thank you. Any questions? Hello.
Can you explain in an intuitive way how a planet can eject a moon? And the same question, how can a spacecraft do a flyby of a planet and pick up speed?
So essentially it's kind of, so ejecting a moon, if we think of Triton with its moon, for example, you think, so what happens is if an object comes close enough to a large planet, compared to that planet, it will have a lot more energy than it need to be caught by the planet. So essentially being captured, we have something called escape velocity. So if your kinetic energy is larger than your potential energy, you won't be captured. So this planet, say Neptune with its moon coming past, Triton and its moon coming past Neptune, if you think of the orbit of the moon going around Triton, you can think of Triton almost going backwards a little bit in their orbit, so the centre of mass will be going through, but Triton might be going backwards just a little bit. The moon will be going forwards, and so that'll be just enough for the gravity of Neptune to hold on to Triton, and for this other moon to be sent out into space. I don't know if that's a very clear explanation, but it comes down to the dynamics of having the energy separating the two.
It seems to us that as it approaches the planet, it speeds up. Then as it passes the planet, it slows down. And the amount of slowing down would be the same as the amount of speeding up. That would
so that's why generally if you...
somehow it ends up with a little bit of excess speed.
Oh, for like a flyby?
Yeah.
Yeah.
This is like they do with spacecraft to give them a boost. Usually was done with a number of them. They use Jupiter to increase the momentum of the spacecraft.
Yeah, so what happens is...
when there's more than two objects.
Yeah. So essentially Jupiter loses that little bit of energy, doesn't it? So Jupiter loses such a small amount of energy that it doesn't notice, but it gets transferred to the other object. So there's quite a bit to it with the physics behind it. I probably can't explain it too well in a short time.
These quasi-moons and mini-moons, how big or shall I say small are they?
Now the mini-moons that we've got at the moment is about 10 metres in size, so very small, about 10 metres. The previous one, CD3, was about 3 metres in size, so very small objects. A quasi-moon probably doesn't really have to have a limit in size. It's just an asteroid essentially that's orbiting around that same area. So they could be maybe 100 kilometres across, a little bit bigger, down to quite small. So I don't think there's any limit to the sizes of them. But the mini-moons have generally been quite small, I think, and they've been very hard to find. But it wouldn't take too much to be a bit bigger than that 10-metre size.
Yeah, I mean, you're describing it as a bus going around the Earth.
Yeah, the one at the moment, like a 10-metre bus, isn't it? Yeah.
So you describe with the detection of the rings, how we see the dipping of the starlight. And that kind of reminded me of how we detect some exoplanets, how it dips the star. But then it kind of made me wonder, we can only detect the rings when they're flat on compared to Earth, because basically the ring dips the light behind it. So could we detect rings that are on different angles?
To a certain extent, so if it was around to a certain extent, but once it was side on, it would be quite difficult. You'd probably, if you were lucky and it was just...
Do we have any ways of detecting those kinds of rings?
I think if the ring was side on and you just saw a little dip in a star once and you kind of followed it a few times, you might be able to develop a pattern of a line for a ring across. So if it's on a 45-degree angle, you could probably still detect them quite nicely. You probably want to get a bit more information to know that it was on the side rather than just, if you only just saw the front and the back, you wouldn't know whether it was face on or on an angle. So you're right, it would take a little bit of extra effort to find those other angles. Yeah.
Could we detect dark matter in the solar system?
Dark matter in the solar system. Dark matter doesn't interact with light at all, so that we wouldn't be able to interact to find it that way at all. Possibly dark matter might only interact gravitationally, in which case we may never be able to detect it, so we have to hope it interacts maybe with the weak nuclear force some other way, but because it is totally transparent to light, unfortunately it wouldn't work. John?
Is there some sort of gap between the Kuiper belt and the Oort cloud?
Yeah, there is a bit of a gap. Just recently, interestingly enough, there's been talk about a possible second Kuiper belt. There's been talk about some other objects being found a bit further out. So there might be kind of like the Kuiper belt, a gap, another Kuiper belt, possibly, and then further out, then the Oort belt. So you're right. So I think an interesting point is that the comets that are 200 years and less than 200 and over 200, you kind of got that 200 plus or minus 10 or 20, where are they coming from? So I haven't seen a plot, but it'd be interesting to see if a plot kind of shows over 200, then nothing, then something again. So that would be an interesting plot to look at. It'd probably give us an idea actually of what might be out there, but there would be a bit of a gap.
The definition of a planet, that third criterion, it's cleared out its neighbourhood.
Yes.
Why don't the Trojan asteroids around Jupiter, what do they count?
Yeah, I guess I guess they're orbiting with Jupiter at a certain distance, but had they been closer to Jupiter, they would be ejected. So they're kind of in a safe area. They're at the Lagrange points, and it's a good question because you kind of think and you look at that the quasi-moons around Earth, it's like, oh, we haven't really cleared that out that well. But I guess there's kind of it must be a cut-off somewhere there. But I know a lot of people aren't happy with that. And I still think that Mercury, if it had a whole lot of asteroids in its orbit, may be pushing its luck being called a planet. So
Category number 2, that point 2, they're not round.
Asteroids?
Yeah.
Oh, I mean, sorry. If Mercury had other asteroids in its vicinity, then Mercury might fail the planet test. Yeah.
Jonathan,
Yeah.
the Kuiper belt is largely formed by the giant planets during the early protoplanetary disk phase, ejecting stuff out.
Yeah.
What about the Oort cloud? Is that
Yeah, that's interesting actually. Yeah, I suppose a lot of that is left over from the protoplanetary disk, but because it's spherical, that's kind of more interesting, isn't it? Because I guess the initial cloud bits and pieces might have been thrown out in different directions. And I suppose also the Oort cloud is really only hypothetical from the long period comets. And because they come from all directions, it kind of points to the idea of a sphere. So I can't really answer exactly why, but I expect just things have been thrown out there somehow. I can't give a good answer to that one.
Questions? Well, thank you very, very much for coming up, Jonathan, this evening for fascinating talk. Things we you don't think about from day to day. So no, thank you very, very much indeed.
Thank you.